Yeah, so welcome back. Today we will be proving two important theorems. Uh, the first theorem tells us that if we have a, a, a convex balanced a local base, then we can get a separating family of seminorms from that. Okay, so theorem. Let X be a TVS and let B be a balanced convex local base of X. By balanced convex local base, balanced convex local base, we mean every neighborhood V of B is balanced and convex. Okay, so let X be a TVS and let B be a balanced convex local base of X. Then we have two assertions. The first assertion tells V is equal to all those X in X such that mu V of X is strictly less than 1. This is true for all V belonging to B. And the second assertion says that this family mu V, where V varies over B, is a separating family of seminorms. Separating family of seminorms such that each mu V is continuous. Okay. So proof let X belong to V, then we know that mu V of X is less than or equal to 1, right, by definition. But we need to show that mu V of X is strictly less than 1. For this we will make use of the continuity of scalar multiplication. We know that 1 times X is equal to X, which belongs to V, right? So by continuity of scalar multiplication, there exists an R positive and a neighborhood U of 0 such that for every beta or for every alpha in K with mod alpha minus mod alpha minus 1 strictly less than R, we have that alpha times X belongs to V, right? This is by the continuity of scalar multiplication. Okay, now take alpha belonging to 1 will it work? 1 minute. Take alpha belonging to 1 minus R comma 1. Okay, take alpha belonging to 1 minus R comma 1, then what do we get? We get 1 minus r is strictly less than alpha is strictly less than 1. Okay, so okay, this will not work, I'm sorry. Take alpha belonging to 1 comma 1 plus r, right? Then 1 less than alpha less than 1 plus r. This implies 1 is greater than or equal to 1 by alpha, that is 1, sorry, 1 is strictly less than 1 by alpha, right? 1 by alpha is strictly less than 1. Right? So we have that alpha times x belongs to v for such an alpha. You take any alpha in this interval, then alpha times x belongs to v, because mod alpha minus 1 is strictly less than r. This implies alpha belongs to 1 by alpha times v, right? This implies mu v of x is strictly less than 1, is less than or equal to 1 by alpha, which is strictly less than 1, which implies x belongs to this set. All those y in x such that mu v of y is strictly less than 1. It belongs to this set. Okay. Now, if mu v of x is strictly less than 1, this implies, excuse me, if mu v of x is strictly less than 1, this implies x belongs to v, right? Why is this true? Because by the remark that we have proven in the previous video, if x doesn't belong to v, then what should happen? Mu v of x has to be greater than or equal to 1, which is not possible because we have taken mu v of x to be strictly less than 1. So mu v of x strictly less than 1 implies x belongs to v. Hence we get the first assertion, that is v is equals to all those x in x such that mu v of x is strictly less than 1. Right? Okay. Now let us prove the second assertion. P. We are showing it is a separating family is very easy, right? One thing, 1 minute. It's easy to see that mu v is a seminorm, right? We have already done the framework in the previous video. V is given to be balanced, is given to be, okay, let v belong to b, then it's given that v is balanced convex, and every neighborhood of 0 is known to be absorbing, right? We have already proved that. Balanced, convex and absorbing. It's and convex, this is given, and we know that v is absorbing. Hence by previous theorem we know that mu v is a seminorm on x. Right? So we need to show that this family mu v where v varies over this base v is a separating family. Is a separating family of seminorms. So let x be non-zero. Since x is a TVS, there exists since x is a TVS, it is housed off, right? So we can separate singleton x and singleton 0, right? Separate singleton x and singleton 0 by open sets. That is, there exists a neighborhood v of 0 such that x plus v intersection singleton 0 plus v is empty, right? Right? Since B is a base, there exists some B belonging to script B such that B is contained in B. This implies singleton x plus B intersection singleton 0 plus B is empty. This implies B is a, notice that this B is a neighborhood of 0, right? This B is a neighborhood of 0, that is 0 belongs to B, and from this we can conclude that singleton x, or it's quite easy right now to see that x doesn't belong to B, right? X doesn't belong to B because the intersection of x plus B and intersection of B, this will be just B, so x plus B intersection B is empty, so, and we already know 0 belongs to B, so x doesn't belong to B. This implies mu B of x has to be greater than or equal to 1, right? Mu B of x has to be greater than or equal to 1. This follows from the remark that we have proven, right? So this shows that mu B of x is non-zero. Okay. So this shows that this family, hence mu V varying in B is a separating family of seminorms. The separating family of seminorms. Okay. Excuse me. Next we have to show each mu V is continuous. To show mu V is continuous. Okay, so let V belong to B and let x belong to x. We have to show mu V is continuous at x. Okay, how do we do this? So we take a neighborhood of mu V of x. So let R be positive. Let R be positive. Consider the open ball B of mu A of x comma R in K, right? This is the open ball in K. To show continuity, we must find a neighborhood W of x such that mu V of W is contained in this ball B of mu A of x comma R, right? If we do this, then we would have shown that mu V is continuous. Right? So let W be equal to x plus R by 2 times V. Okay, V is a neighborhood of 0, R by 2 times V is also neighborhood of 0, and x plus R by 2 times V is a neighborhood of x. Is a neighborhood of x. Let y belong to x plus R by 2 times V. This implies y minus x belongs to R by 2 times V. This implies mu V of y minus x is less than or equal to R by 2. Okay. Now we want to show we want to show this, to show mu v of y belongs to this ball B of mu a of x comma r, to show this. So let us estimate mu v of y minus mu v a of x. This, by the property of seminorms, is less than or equal to mu v of y minus x, right? And this is less than or equal to r by 2, which is strictly less than r. So this shows that mu v of y belongs to the ball around mu a of x of radius r. Right, this is true for all y in W, or this is true for all y in this set, right? Hence, the image of this open set is contained in this ball, right? This implies mu v is continuous, right? Mu v is continuous at x. Since our choice of x is arbitrary, we get that mu v of x is a continuous function on capital X. Is it okay? So next, the next theorem is a converse of the previous theorem that we proved. In the previous theorem, we showed that if we have a local base, wait 1 minute. Excuse me, yeah. So if we have a topological vector space and we have a balanced convex local base of x, then we get a separating family of seminorms. We will be proving the converse of this theorem. That is, if we are given with a if we have a vector space x and we are given with a separating family of seminorms on x, then we can convert x into a topological vector space. Not any kind of topological vector space, a locally convex topological vector space. That is, we can find a local base of x whose each element is a convex neighborhood of 0. Okay, so we will be proving the converse of this theorem. The converse is the proof is little involved. So theorem. So let us start theorem. Let x be a vector space over K, and let P this is some family of seminorms. I is the indexing set, it can be anything, be a separating family of seminorms on X. So you are given a vector space over K and you are given a separating family of seminorms on X. Now define the set Vp comma n as, okay, before that, sorry, let P belong to P and let n belong to n. Define V of P comma 1 by n as all those x in X such that P of x is strictly less than 1 by n. Let script S be the collection of all such sets. Okay, Vp comma 1 by n, where P varies over P and n varies over n. So Vp, this set S is a collection of all such Vp comma 1 by n, where P is varying over P and n is varying over n. Now let B be the collection of all finite intersection of elements of S. Okay, let me write it in a set notation. Let B is the collection of all finite intersection of members of S. Then, so this was the hypothesis of the statement. Then B is a balanced convex local base for a topology tau on X such that X with this topology tau is a topological vector space. Okay, this topology will be a vector topology, and X with respect to this tau is a topological vector space. Moreover, each P belonging to P is continuous with respect to tau, right? Okay, so let us start the proof. So I am defining tau like this. Define tau as all those subsets of X such that A is a union of translates of members of B. Okay. For example, we say A belongs to tau if A is the union of translates of members of X alpha plus some W alpha, X alpha plus W alpha, alpha varying over some indexing set J, where X alpha belongs to X and W alpha belongs to script B. Okay, so your set a set in X is open if and only if it is a union of translates of members of B. Union of translates of members of B. Right? Do you understand the topology? We take the translates of members of B, then we take the union, right? So I am defining my topology like that. So it's quite clear that tau is a translation invariant topology. So it is clear that tau is a translation invariant topology on X. Translation invariant topology on X, right? Okay, we need to show that X with this tau is a topological vector space. So to show that X with this tau is a TVS, right? So what do we need to show? We need to show that singletons are closed and the addition and scalar multiplication maps are continuous, right? So first we show that First we show that singletons are closed. Singletons are closed with respect to tau. Okay, singletons in X are closed. Singletons in X are closed with respect to tau. Okay. Yeah, excuse me. So let X belong to X. Let X belong to X. How do we show singletons are closed? To show that singleton X closure is equal to singleton X. So in other words, we have to show that in other words, we have to show that if we take any y in X such that y is not equal to X, then this y doesn't belong to X closure. If we show this, then we are done, right? Then X closure will be equal to X. So let us start. Let y belong to X such that y is not equal to X. This implies y minus x is not equal to 0, right? Y minus x is not, y minus x is not equal to 0. Okay, we need, okay, this also implies x minus y is also not equal to 0, right? Since P is a separating family, of seminorms, since P is a separating family of seminorms, there exists some P in P such that P of x minus y is P of x minus y is non-zero, right? P of x minus y is non-zero. This is by the definition of separating family. You can find P in P such that P of x minus y is non-zero, right? Okay. Now there exists an n in n such that what happens? This is a real number, right? This is a positive real number which is not 0. That is P of x minus y is positive, right? There exists an n in n such that 1 by n is strictly less than P of x minus y, right? This is again by Archimedean property. There exists an n in n such that 1 by n is strictly less than P of x minus y. This implies x minus y or greater than or equal to 1 by n. This implies x minus y doesn't belong to Vp comma 1 by n. Vp comma n, right? This implies x doesn't belong to y plus Vp comma n. This implies x belongs to V plus Vp comma n complement, right? This is open by definition, and we have added translates of Vp comma n as open sets, right? So this is an open set and the complement of that is closed. This implies singleton x, okay, this implies singleton x is contained in y plus vp comma n complement. This is closed, right? This is closed subset. This implies singleton X closure is contained in y plus vp comma n complement, right? This implies what? X closure intersected with singleton y is empty, right? Because X closure is contained in the complement, right? And singleton y is contained in this set, right? Y plus vp comma and 1 by n. Singleton y is contained in this, and X closure is contained in singleton X closure is contained in the complement of this set. So X closure intersection y singleton X closure intersection singleton y is empty. This implies y doesn't belong to singleton X closure. This implies singleton X closure is equal to singleton X. So we have shown that singletons are closed, right? Next we need to show that addition and scalar multiplication are continuous. Okay. So let x comma y belong to X, and let W be a neighborhood of 0. This implies x plus y plus W is a neighborhood of x plus y. These are the only neighborhoods of x plus y of this form, right? You take any neighborhood of 0, you add x plus y to that. These are the only neighborhoods of x plus y. This is by the definition of tau. Right? Okay. Now, since B is a base, B is a local base of tau, there exists some u, say v of pi1 comma 1 by n1. Okay, let me write in the next line. There exists u of the form v pi1 comma 1 by n1 intersection v pi2 comma n2 intersection v pik comma 1 by nk, such that u is contained in W, right? This is by the definition of local base. So the natural choice would be v equal to v comma pi comma 1 by 2n1 intersection pi2 comma 1 by 2n2 intersection pik comma 1 by 2nk, right? Then it's easy to see that v plus v is contained in u, right? So for example, let me show this. Let u belong to v and let small v belong to v. Then what do we have? Pij of u is strictly less than 1 by 2 nj, and Pij of v is strictly less than 1 by 2 nj. This is true for all j varying from 1 to k. J is varying from 1 to k. Then what happens to u plus v? Pij of u plus v is less than or equal to Pij's are seminorms, right? So Pij of u plus Pij of v, which is strictly less than 1 by 2 j nj plus 1 by 2 nj, which is equal to 1 by nj, right? That is u plus v belongs to u, right? U plus v belongs to u. So we have shown that v plus v is contained in u. Hence x plus v x plus v sorry x plus v plus, okay, there's something wrong, plus y plus v is equal to x plus y plus v plus v is contained in x plus y plus u, which is contained in x plus y plus w, right? So this is a neighborhood of x, this is a neighborhood of y, and we have shown that x plus y x plus v plus y plus v is contained in x plus y plus w, right? So this implies addition is continuous, right? Next is the little tricky part to show scalar multiplication is continuous. To show scalar multiplication is continuous. Okay, I forgot to show sorry, we also had to show that this collection Vp, 1 by n is balanced convex, right? It's quite easy. Okay, let us do that. And right, let us show it's balanced. To show balanced, and before doing this, let us do this balanced and convex to show these are balanced and convex. Okay, so let mod alpha be less than or equal to 1, and let x belong to Vp, 1 by n. Then p of x is strictly less than 1 by n. What about p of alpha x? This is equal to mod alpha times p of x. This is strict, since mod alpha is less than or equal to 1 and p of x is strictly less than 1 by n, we get this is strictly less than 1 by n. So this implies alpha x belongs to Vp, 1 by n. This implies Vp, 1 by n is balanced, right? Vp, 1 by n is balanced. Even convexity is very easy to show. Let x, y belong to Vp, 1 by n, and let t belong to closed interval 0, 1. Then p tx plus p of tx plus 1 minus t times y is less than or equal to t times p of x plus 1 minus t times p of y, right? This is strictly less than t by n plus 1 minus t by n, which is equal to 1 by n, right? This implies tx plus 1 minus t times y also belongs to Vp, 1 by n. This shows that this is convex. One fact that we will need to show scalar multiplication is continuous is as follows. Like, okay, let t be positive, then we need to show that t times v is continuous, is open. We need to show that TV is open. It's not clear from the definition why TV should be open, right? You need to prove it, because we are multiplying with some arbitrary positive real number. What is t times, okay, what is v? Sorry. Need to show that t times v, p, n is open. Right? We can do it in a more general setting. T times Vp, okay, let me write it like this: intersection of t times v pij comma nj, j varying from 1 to k. We need to show that this is open. It's not clear from the definition why this is open, right? So let y belong to intersection of j varying from 1 to k tv ij times nj. What does this mean? Y belongs to tv times pij comma nj. But what is t times vij comma? This is t times all those x such that x belongs to, okay, let us write separately. Before doing this, let us understand what is t times vpij. T times vpij comma nj is t times x such that x belongs to vpij comma nj, right? This is actually equal to all those x in x such that pij of x is strictly less than t by nj. Do you see that? So let us take a z in. To see this quickly, let us see this. Let z belong to let z belong to t times v pij comma nj. Then z is equals to t times x, where x belongs to some, for some x, pij comma nj. This implies x is equals to z by t, right? Mu, oh sorry, not mu, sorry, pij of x is strictly less than 1 by nj, but this is nothing but pij of z by t is strictly less than 1 by nj. This implies pij of z is strictly less than t by nj. Using a similar argument, you can show element in this is contained in this, right? So it's quite easy, right, to see t times vij, t times v of pij comma nj is this set. I hope you will be able to do that. So let y belong to this set. This implies, so coming back, implies pij of y is strictly less than t by nj for all j equal to 1 to up to k, right? Next, how do we do this? So let choose 1 by mj, or choose mj in n such that pij of y plus 1 by mj is strictly less than t by nj, right? I can always choose such an mj, right? I am choosing mj so small, that pij plus pij of y plus 1 by mj is still strictly less than t by nj. I can always do this by Archimedean property, right? Now take this set, this open set v of pij comma 1 by mj, j varying from 1 to k, y plus this set. Okay, this is an open set containing y. This is a neighborhood of y, right? This is an open set this is a neighborhood of 0, and you are adding y to the neighborhood of 0. So this is a neighborhood of y. We show that this neighborhood is contained in this set is contained in this. Okay. So it's a neighborhood of y, right? So let z belong to y plus intersection j varying from 1 to k v pij comma 1 by mj. What does this imply? P of z pij of z minus y, pij of z minus y is strictly less than 1 by mj, where j is from 1 to up to k, right? We know that pij of z minus pij of y is less than or equal to pij of z minus y, right? This implies, this is by properties of seminorm, pij of z is less than or equal to pij of z minus y plus pij of y, which is now this is strictly less than 1 by mj plus pij of y. Now we made a choice of this mj such that this is satisfied, right? Pij of y plus 1 by mj is strictly less than t by nj. So we get that this is strictly less than t by nj. What does this mean? This means that z belongs to intersection of t times v of pij comma 1 by nj, j varying from 1 to k, right? This implies this open neighborhood of y, this neighborhood of y is a subset of this set, right? This set. Right, so we have shown that if we multiply t positive to elements of B, so if we multiply t positive to members of B, they still remain to be open neighborhoods of 0. Remain to be neighborhood of 0, right? This is what we have shown. So now we are in shape to prove scalar multiplication. So that was the main goal, right? So let alpha belong, okay, to prove scalar multiplication. To prove scalar multiplication is continuous. Let alpha belong to k and let x belong to x, right? Okay. Let w be a neighborhood of 0, hence alpha x plus w is a neighborhood of alpha x, right? This is by the definition of our topology. Now, like in the argument for scalar addition, there exists some u, right, which is of the form v p I1 comma 1 by n1. Oh, I've made a big mistake by changing the notation here. I am so sorry. uh, okay okay, I've changed it here as well. Okay, there is a okay, I've changed it here as well. Okay, this is how we define Vp comma 1 by n. So okay, there is a problem here. This is 1 by n, not 1. Sorry. I have confused you with my notation. I'm sorry. Okay, this should be 1 by n. Sorry. Okay, here it's fine, everywhere it's fine. Okay, for addition it's fine. Scalar multiplication. Okay, here I made a mistake. I changed the notation again. Sorry. This is 1 by n. This is 1 by n. Okay. Yeah. Right. So coming back, I'm sorry for that confusion of notations. So let w be a neighborhood of 0 and alpha x plus w is a neighborhood of alpha x. Then since b is a base, there exists u of the form v p1 pi1 comma n1 1 by n1 intersection vpik comma 1 by nk such that u is contained in w, and let v be equal to this, right, what we did in addition. V be equal to pi1 comma 1 by 2n1 intersected with vpik 1 by 2nk. Just one more time, I'll just check if everything is okay. Yeah, this is how I've defined. Right. Okay. So let v be this. Then we saw that v plus v is contained in u, which is contained in w. Right? Okay. So now it's easy to see that v is absorbing, right? Okay, we have to show there exists some s positive such that x belongs to s times v. Okay, so how do we do this? Consider pij of x, right? Now this is greater than or equal to 0, so there exists some sj positive such that pij of x is strictly less than sj. Let s be the maximum of all these things, s1 up to sk. Then pij of x is strictly less than s for all okay, one minute, this is not correct. Sorry. Yeah, so why does such an S exist? Now consider Pij of x times nj, right? This is greater than or equal to 0, right? So there exists some sj positive such that Pij of x times nj is strictly less than sj, right? This is by Archimedean property. We can find some big real number such that this happens. This implies Pij of x is strictly less than sj by nj. Now let S be the maximum of all these sj's, s1, s2 to sk, right? This single s works for each of them, right? Pij of x is strictly less than s by nj for all j varying from 1 to up to k. This implies x belongs to s times s times v. Is it okay? This shows that x belongs to s times v. Okay, now let t be equal to s by 1 plus mod alpha times s, right? Let t be equal to s by 1 plus mod alpha times s, and this t is positive, right? Now consider x plus t times v. T times v is a neighborhood of 0 and x plus t times v is a neighborhood of x. Okay, and let beta belong to k be such that mod beta minus alpha is strictly less than 1 by s. My claim that for every y in x plus tv, beta times y belongs to alpha x plus v, right? And we know alpha x plus v is contained in alpha x plus u, which is contained in alpha x plus w, right? So if I show beta y belongs to alpha x plus v for all y in x plus ty and for all beta such that mod beta minus alpha is strictly less than 1 by s, then we would show that this scalar multiplication is continuous, right? This is by the definition of scalar multiplication. That would be right. That would imply continuity of scalar multiplication. Okay, so let y belong to x plus tv. This implies y minus x belongs to tv. Okay, now consider this beta y minus alpha x. I add and subtract beta x plus beta x minus alpha x. This is equal to beta times y minus x plus beta minus alpha times x, right? Now I multiply and divide by mod beta. Okay, so we get beta times mod beta times beta y minus x plus beta minus alpha by mod beta minus alpha times mod beta minus alpha times x, right? I've added and okay, here there is a mod, sorry. So I have multiplied and divided by mod beta and multiplied and divided by mod beta minus alpha, right? Okay, now what? note that V is balanced, right? V is balanced, hence T times V is also balanced. So is S times V. So is S times V, right? T times V and S times V are both balanced. You can easily show that. It's not that hard. And X minus Y belongs to T times V, right? X minus Y belongs to T times V, right here. Sorry, Y minus X belongs to T times V. So we have Y minus X belongs to T times V and T times V is balanced. This implies mod, this implies what? This implies beta by mod beta times Y minus X belongs to T times V, because T times V is balanced. And we also have this extra mod beta here, so hence beta by mod beta times mod beta times Y minus X belongs to T times mod beta times V, right? Because this belongs to this vector belongs to T times V, mod beta times that vector belongs to T times mod beta times V. Okay, what do we have here? We have X belongs to S times V, right? X belongs to S times V. We have X belongs to SV. Where is this coming from? From here, right? Here X belongs to S times V, right? S times V is balanced, right? S times V is balanced. This implies beta minus alpha by mod beta minus alpha times X also belongs to S times V, right? And we have a extra sorry, not this. We have a extra mod beta minus alpha. So this hence beta minus mod beta minus alpha times mod beta minus alpha times X belongs to mod beta minus alpha times SV. So finally we have this, right? This expression. Let me write it again. Beta minus Y minus alpha times X. Is it correct? Yeah, beta minus Y times alpha times X, which is equal to beta by mod beta times mod beta times, let me rewrite, yeah, Y minus X plus beta minus alpha, sorry, beta times X is contained in, see here, the first term is contained in T times mod beta times V, T times mod beta times V, plus the second term is contained in mod beta minus alpha times S times V, right? Observe that mod beta minus alpha times S is strictly less than 1. Why is that? That is by the choice of beta, right? We chose beta in case such that mod beta minus alpha is strictly less than 1, right? So this is this product is strictly less than 1 and V is balanced, hence mod beta minus alpha times S times V is contained in V, right? What about this now? T times beta. What about T times beta? What about T times beta. Note that T times mod beta, right? Yeah, T times mod beta, sorry. What is T? What is T? T is this number, right? This is what we have taken T as, right? T is S by 1 plus mod alpha times S. So this product becomes mod beta times S by 1 minus mod alpha times S. Now let us find a bound for mod beta. Mod beta minus mod alpha is less than or equal to mod beta minus alpha, which is strictly less than 1 by S by the choice of beta, right? This implies mod beta is strictly less than 1 by S plus 1 by alpha. Now substitute this here, we get T times mod beta, which is equals to mod beta times S plus 1 minus 1 by 1 plus alpha times S, which is strictly less than 1 by S plus mod alpha times S divided by 1 plus mod alpha times S. This is equal to 1 plus mod alpha times S by 1 plus mod alpha times S. Everything is nicely chosen so that this is equal to 1, right? This is equal to 1. So we get that T times mod beta is also strictly less than 1, and since B is balanced, we get that since V is balanced, we get that T times mod beta times V is strictly less than V. Hence we get beta y minus alpha x, which is contained in what? This. What did we get here? We got this, right? Beta minus alpha x is contained in this. T times mod beta times V plus mod beta minus alpha times SV. And what did we show here? We showed that this is contained in V and this is contained in V. So we get this is contained in V plus V. This by choice is contained in U, right, which is contained in W. This implies beta y is contained in, belongs to, this is wrong notation, belongs to alpha x plus W, right? So this shows the continuity of scalar multiplication. Finally, we have to show each seminorm is continuous. Each seminorm P is continuous. P in P is continuous with respect to tau. Right? Okay. So let x belong to x and let B of P of x comma R be a ball in K, be a open ball in K. Choose 1 by n, choose n in n such that 1 by n is strictly less than R, right? We can always do this by Archimedean property. Consider Okay, choose m belonging to n such that 1 by n plus 1 by m is strictly less than r. Right, we can always do this again. We're choosing very small m. Consider x plus vp comma 1 by m. Right, will this work? Okay, you don't need this, I think. Sorry. Okay, consider, let us check if it works. Consider vp comma 1 by n. This is a neighborhood of 0. Neighborhood of 0. Okay, this may not work. 1 minute. Let me see. I'm not sure if this will work. Consider vp comma 1 by n, which is a neighborhood of 0. Then x plus vp comma 1 by n is a neighborhood of x. Let y belong to x plus vp comma 1 by n. This implies y minus x belongs to vp comma 1 by n. This implies p of y minus x is strictly less than 1 by n. Yeah, okay, this will work. Then mod of p of y minus p of x is less than or equal to p of y minus x, which is strictly less than 1 by n, which implies p of y belongs to the ball p of x comma r, right, which is 1 by n is chosen such that it is strictly less than r. 1 by n is strictly less than r, right? So p of y belongs to the ball of p of x comma r. Hence image of this open neighborhood v of x plus v of p comma 1 by n under p is contained in this ball p of x comma r. This implies p is continuous at x. Since x is arbitrary, we get that p is continuous on x. So this completes the proof. It's a lengthy proof, it's a bit involved, and I hope you'll go through the proof again to understand some intricacies. So thank you.